Welcome to problem solving session for Introduction to Group Theory. I am Siddhi Balu Ambure from IIT Gandhinagar, and today we will discuss problems related to topics covered in this course. It will be miscellaneous. We will be covering. We will try to do questions from various different topics, and we will try to see how many topics we can cover. If you have any doubts, you can definitely ask. So let us start with the first question. Question 1, that how many groups of order 320 exists up to isomorphism? This is our question. And if you remember what we learned yesterday from structure theorem, this is basically application of structure theorem, what we discussed in problem solving session for week 12. I'll just repeat that, and a quick I won't be writing this in detail. So G is abelian group, we know, and if cardinality of or order of G is n, and n is equal to p1 power alpha 1, p2 power alpha 2, pt power alpha t, is prime factorization of n, then we have these things. First one is that G then will be isomorphic to G mod P1 power, yeah, sorry. G will be isomorphic to G1, G2, let me write G2, up to GT, the number of primes available in the prime factorization of G, where the order of each Gi is this P I power alpha I. And the second thing we know is that this Gi is isomorphic to Z power Pi alpha I. So I will write the notation. So notation we will use is Z mod Nz is, or Zn is Z mod Nz. Okay, this is the notation. So this is P I power alpha I1 cross ZP power I alpha I2, and so on up to Z Pi alpha I Ti, where this, as we know, this Pi1, sorry, alpha I1, alpha I2, alpha ITI is a partition of this alpha I. And when I say partition of this alpha I, means that it is the summation alpha I j from 1 to this Ti is actually alpha I. Okay, this is what it means. And this is the information we have. So we want, so every abelian group of order, yeah, this is abelian group. Okay, the how many abelian groups is the correct way of it. Let me just shift this. Abelian, okay. Yes, and this is what we have. So 320. So we will see how to use this theorem. We saw example yesterday also where we explicitly saw the group was given and we were asked whether the given groups in the options are isomorphic to the group given in the question or not. So right now we are trying to find the number of elements uh, in this uh, sorry, number of groups we of order 320 which are isomorphic to which are isomorphic to uh, number of abelian groups of order 320 up to isomorphism. We are trying to find the number of such abelian groups of order 320. So here we need to write first the prime factorization of 320. So this is 2 power 5, this is 2 5. So this is 2 power 6 into 5. And here we have to look at the partition of this alpha i's. So partition of alpha I. So here my alpha 1 is 6 and alpha 2 is 1. So for 5, so this will be isomorphic to g1 power some 2 power alpha. This is G1 cross G2, and G2 is what? G2 was some ZPI cross ZP, sorry, Z pi power alpha 21 up to Z5 power alpha some 2 I2. But here the only possibility for partition of 1 is just 1. So the G2 will always be, this will always be Z5. Okay, we don't have any other possibility for G2. So what we need to do is we have to find all the partitions of 6, and according to them, then we will be getting, so we have to find this. We have to find the, or we have to, we have to find how G1 looks like in this case. So G1, so to find that, we need to find the partition of 6. So how to partition 6? 6, as I told you yesterday, the partitions of 6 are, I have 6, then 5 plus 1, then 4 plus 2, then 4 plus 2, 1 plus 1. There are quite many of them, but yeah, let's see. Then 3 plus 3, 3 plus 2 plus 1, 3 plus 1 plus 1 plus 1, right? Then 2 plus 2 plus 2. So when we go on writing this partition, to avoid the repetition, we always look at the decreasing. For example, here 2 plus, if I write 4 here, then that partition is already covered here. Okay, so always this decreasing of number. So here after 5, I am writing 1, 4, then 2. I am not going to anything which is greater than. For example, here after 2, I went down to 2 and not something greater than 2 or that kind. So that we need to take care of. 1 plus 1, then this is 2 plus 1 plus 1 plus 1 more. Let me shift this. And one more partition left, that's it. it will be 1 plus 1 6 times. And these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are 11 partitions. And so corresponding group here will be this Z2 power 6 and not into product with Z2 power 5. So that is Z32 into not 32, 64, right? Yeah, Z64 product with 5. And similarly, I'm directly writing this. So this will be Z32, 2 power 5 will be 32 into Z2. I mean, Z32 product Z2 product Z5. Similarly, here Z16 Z2 square. So it is 4 product Z5. Here Z again 16 Z2 cross Z2 cross Z5. Here it is Z6. I mean, we are anyway asked the number of such groups. So here definitely the answer is 11 because we got 11 partitions of uh, 6 and that's how it is. So if you were asked to, so we will do that further. Let me just finish this. This is Z8 in Z8 cross Z8 cross Z5. This is Z8 cross Z4 cross Z2 cross Z5. This is Z8 cross Z2 thrice cross Z5 and here Z4 Z4 cross Z4 cross Z5 here. Yeah, here again it is Z4 cross Z4 cross Z2 cross Z2 cross Z5 and here again Z4 cross and then 6 times Z2. Yeah, Z2 cross. And these are the 11. These are the only 11 possibilities for this. So how many abelian groups of order 320 exist? So these are the only possibilities. Okay. And now similar to this, I am just adding on to this problem which we solved here. So instead of 320, if the question was, yeah, how many how many abelian groups of order 310 exist up to isomorphism? So in that case, what you can do is that you will again use structure theorem and you will write the prime factorization of this 310. So this is 31. So this is 2 into 5 into 31, right? This is the prime factorization of this group. Oh, sorry, of this n. And every prime has exponent 1 here. So what we can get from here is that the only possibility, only group exists of this order is this Z2 cross Z5 cross Z31. Only by structure theorem. This is the only possible group, right? But also, and this is nothing but just this Z310. Okay, this group has element of order 310. Sorry, this is 31. Okay, we saw that yesterday that and this we know is cyclic. This is cyclic group. So from here one can also conclude that if at all if there exists a abelian group of order 310, then this is the only possible group and it is cyclic. So if you might also be asked question like uh, a, gr- a group of order 310 is, in the options you might have cyclic, abelian, and I mean normal, uh, and so on. Uh, Not normal, I mean simple, and so on. So such kind of questions, uh, I mean there are possibility of such kind of questions to be asked in the exam. So be prepared for that. So for example, for this 310, we saw that there is only cyclic group possible because of its because what we got here, it is isomorphic to 310, and that's it. And apart from this, what we can, yeah, let me, sorry. And apart from what I was saying is, yeah, apart from this, what one need to understand is if I have, yeah, this was the one thing which I wanted to point out here, that if you have this kind of, what I'm saying, group G of this kind, then yes, this is the only possibility. And yeah, this one for the exponent of the group. So I'm just writing thing for the exponent of the group. Group G exponent means n in n such that G power n for all G in G, G power n is identity. And this we saw that it is this n is then LCM of this n1, n2, and nt. You can keep this in mind and you can try to do as many examples as you can using this. So smallest n. So that's it. So abelian group of order 310 is always cyclic. We got it from this example because 310 is also a group and of order 310. This said 310. And this is a group which we got from structure theorem. And by structure theorem, this is the only possibility. So we got that this is the only possible group of order 310 we can have. And now this is something which we tried to do in, I think, tutorial 10, yeah, which was left as an exercise. So this epsilon, this is my exponent of G. Yeah. So this question is something which we left the other day. So what we had was the G was let G be a group of order PQ where P and Q are primes, and I have with Q less than P, and this let H is equal to X with order of X is P and K is Y with order of Y. So when I say K is Y, I mean cyclic group generated by Y in G. And it is of order Q. And H is cyclic subgroup. Sorry, H is normal subgroup of G. And then we have, I mean, you can refer to this question from tutorial 10, okay? Refer tutorial 10 for this question. I'm just writing down all the things which we did there. And we had this, that yxy inverse is some x power I. We were in this situation and we had to prove that this y power r x y power minus r is x power I power r. So this is I power r. So for example, for r is equal to 2, this is x I square, x power I square. This is what we wanted to prove. Then prove this. We have to prove this. And so let us do with the how to prove. I'm doing this because we could not do it the other day. Sorry. So how to proceed with this is, we have this y inverse is x power I, right? So for 2, what I will do, this is y into y inverse, y inverse. This is what? This is x power I. Sorry. This is x power I y inverse, right? And this I can write as yx y inverse, yx y inverse, so on up to yx y inverse. And this is I times. So what I'm doing is, so this is y x x x x y inverse. This is I times. So I'm just multiplying in between this with I. And what I get here, for each this yx y inverse, I have this x power I. So this is x power I. The second one is x power I. So on up to x power I here. Right? These are I products. So for each such pair here, I'm having this x power I. And when I do this, this is what? This is I plus I plus I. And now this is I times. So this is what? X power I into I. So this is x I square. Okay, I hope you got. And what is on the left hand side here? This is y square, x y inverse square, which is now what I got is y x power I square. And this is what we wanted in that proof. And we used it to prove the statement that G is a product of this H and K. Okay, so, and we can continue this process here. We got this. Now, again, what I will do is, what we can do is, this is Y y square xy square and then y inverse, and let us try this. And this is y x I square y inverse. Okay, and then what I will do is, yeah, then again we can split them, and this will again be, let's try to do this. I want one more I. So this is y, yeah, we can do this. This is y x y inverse, and so on up to y x y inverse. And this I will get how many times? This will be I square time. Wait, me to write y x y inverse, so on up to y x y inverse. This is each is this is I square time, and but each of this is x power I, right, from the given condition. So x power I, this is now I square times. So if I club them, so this is what? This is x power I, and this is I square times. So this is x power I in I square I. So this is x power I cube, and this is what we wanted to do here. So that therefore we get this as y cube x y cube inverse as x power I cube. And you can proceed like this. So for since R is finite, in fact R here, if you go back and see the proof, this R was less than equal to P. I mean, we can definitely, in fact, Q. This R here was less than equal to Q. So this is finite process, and you can just continue to do this. And every time we split, we will be doing this transition here. And forget about this. If we do the induction, what we will have is x y power r minus 1 x y power minus r minus 1 is equal to x power I power r minus 1. And then what I will do is again multiply here by y, here by y inverse, here also y, and here by y inverse. And I will split each of this x r minus 1 times. And then each of this r minus 1 pair will be giving me x power I. And then this will be x power I, how many times? I power r minus 1 times. And then this will give me that it is x power I power r. Okay, I hope this is clear. And you can just uh, understand this. So this was the proof which we left back then when we were doing that, when we were doing assignment 10. And this is next question. I think this is fourth. This one was three. Yeah, this is fourth. that let G be a non-trivial, that is not a unit, not the identity, element in this automorphism group of Z8, then question is, what is the order of G? And again, as we have used this multiple times, this automorphism group of Zn is isomorphic to Un. And this is what is a x n bar, m bar, or maybe x bar in, no, a bar in Zn, such that GCD of A and N is 1. Okay, so here what we want to find is out of Z8. And so this is isomorphic to, by this result here, this is U8. And this is all those collection of A bar such that GCD of A and 8 is 1. So the only possible choices here we have are 1 bar, 3 bar, 5 bar, and 7 bar. You can check this because GCD of 2, 8 is 2, 4, then 3 again we have here, 4, 8 is 4, and 6, 8 is 2, and so on. So we want GCD 1 element. So these are the only 4 elements. So we are asked if I choose any non-trivial element. So any non-trivial elements means any non-identity element. So we have choice of 3, 5, 7. And we will check for each of this element that 3, for 3, 3 square is 9. So 3 bar is 9 bar. That is 1 bar in Z8. Similarly for 5, this is 5 square. That is 25 bar. That is again 1 bar in Z8 because 24 minus 1 will give me 25 congruent to 1 mod 8. Okay, and for 7, or maybe write this, that 7 square is 49 bar. That is again, it is 48 congruent to 1 in Z8. 49 is congruent to 1 uh, mod Z8. Okay, so that's why every element here has order 2. So therefore, here the answer is 2. And that's how. Any given Zn, you have to just calculate this. For example, instead of Z8, if I was given any other number, for example, Z15 or any such number. So let us calculate for that. Out of Z15 is U of Z15. So that is, I want to choose all the elements such that GCD of N and 15 is 1. So this will contain 1 bar, then 2 bar, 4 bar, 6 won't be there, 7 bar, 8, 9 won't be there, 10 won't be there, 11, 12 won't be there, 13, and 14. Okay, so what is this group? This is group of order 1, 2, 3, 4, 5, 6, 7, 8. Is this correct? Okay, so it has 8 elements, and we can see what is the order of each of such element. So here, order of 8 is, you can, check. We need to check. You can ask, the question can be asked like, what is the maximum or minimum possible order of a given element in this ort Zn? So, for example, here the group was isomorphic to K4 and every element had order, every non-trivial element had order 4. So we could, so answer here was 2 um, for any non-trivial element. But in general, not all the groups, all the elements in the group can have same order. So you, in that case, you can just see what is the maximum possible order or minimal is there. For example, here 8 into 8 is 64, that is minus 1, that is 14. We need to just find, we will just do for few numbers here. So for example, order of 2 square is 4. For example, 2 power 4 is 16, which is congruent to 1 in Z 15, right? So order of 2 here is 4. Order of 4 here will be 4 square, that is 16. Then 1, that is order of 4 is 2. Order of 7 is 7 square is 49, and 49 under 50 is 4 bar. And then now the moment I have 4 bar here, I will have to now multiply it twice. Okay, 7, or let me just multiply it one more. 7, so this is 4 bar. Now 7 cube is 4 sevens are 28, which is under 50. It is 13 bar, and 13 into 7, or we can just write this as minus 2 bar, doesn't matter. Let me write this as minus 2 bar for simplicity. So 7 4 is 7 into minus 2 bar. So that is minus 14 bar. But 14 bar is minus 1 bar in Z15. So I get here 1 bar. Okay, from here itself, since 4 has order 2, you could have understood that this thing we need to raise it to power 2 to get. So what from here, what I was saying is that I know that 7 bar is 4 bar, but order of 4 bar is 2. So this will give me 7 bar as 4 bar square, that is 1 bar. That's what I was implying here. Okay, it doesn't matter. We anyway got the answer. Similarly, we can do for 8 and other numbers. Let me just do this. Yes, only 4 are left. Okay, 8. 8 bar square is 64. So 64 is minus 1. No. It is again 64 is 4 bar. So again, this 8 square is 4 bar square, which is, we know, 1 bar. So that's why we get that order of, here order of 7 was 4, here order of 8 is 4. Again, I want to find now order of 11 bar. right? Yeah. So 11 square is 121. So directly we get 1 bar here. That's not a problem, right? Because 15. And then order of 13 bar, which we need to find. So 13 square is 169 bar. And 169 under 50 is 4 bar. And again, then 13 square will be 4 bar square, and this will be of order 4. Sorry, this is 1 bar, and this will give order of 13 to be 4. Here order of 11 was 2, and now order of 15 bar, sorry, 14 is 14 square is 196, and this is 50 plus 30, 65. 150, then 190, 180. Yeah, so this is directly 1 bar. So order of 14, that's why is 1 bar here, right? 195 is divisible by 15, right? It is 150 plus 46. 46 is congruent to 1 mod 15. So yeah. So this is 1. So order of 14 is that's therefore 2. So we got what this 1, 2, 3 elements of order 4, and rest were of order 3 elements of order 2, and rest were of order 4. And so whatever. So that's how you can. So maximum possible order in this case is 4, and the minimal possible order in this case is 2. So, and yes, when you are asked to find the minimal or maximal order, the minimal order will always be 1, because order of identity element is 1. So when such, I mean, here also they mentioned that non-trivial element. So yeah, the minimum possible order for any given group, for any given non-trivial element, will always be greater than or equal to 2. Please be mindful when you read the question. Okay, so this is what we have here. So now let's move to next question. Yeah. Question 5, that let J be a group, be an abelian group of order 120, and let H and K be subgroups of order 5 and 24, then G is isomorphic to H cross K. And this is the question they have asked. So if you want to use structure theorem here, so this 120 is, wait, so this is 2 cube 3 into 5, right? So 5 has partition only 1, and so we have to deal with this. So any group will be of this order, right? Sorry. So G will be isomorphic to G1 cross G2 cross G3. And here by default, I will have this, if I club them as H, then this will be H cross Z5. Right, H and K are subgroups of order 5 in G. So subgroups of order 5 in G means this H is anyway cyclic, right? So H is subgroup of order 5. So this implies this H is anyway isomorphic to Z5. This is the only possibility for group of order 5. Okay, so this is there. So now we have to see, not H, this is really bad notation. Let me write K, or let us keep this as G prime, some G prime. G prime cross Z5. And what here they have said that this K is a group of order, this G prime will be of order 24. Order of G1, G dash here, or this G prime will be 24 because we are dealing with the group of order 120. So this will be group of order 24. And note that here they have said that K is a group of order 24, and this intersection of H and K will be just identity element. Please understand this, because if at all they have any some A belongs to H intersection K, then in that case this A belongs to H, so order of A will be 5. Okay, some non-trivial element if I choose. And also, if that is the case, this A also belongs to K. This implies order of K, order of this A will divide order of K. So this implies that 5 divides 24. So this is contradiction. So only possibility of this H and K, sorry, not the only. So intersection of this H and K is just identity element. So therefore this K here, therefore this G has to be isomorphic to this H cross K, because this is group of order Z5 and this group of order 24 is what this K actually is in this case. So K, the only we just saw that H intersection K is not possible. So this G has to be cross product, the direct product of these two elements, these two groups, one of order 5 and the other of order 25. We started this information, first we got this using structure theorem. Then we saw here that this is identity, so that overlapping is not possible. For example, I can choose, for example, if I take Z8, and I can say that H and K are a group of order 2 and K is group of order 4. There is very well possibility that H could be contained in this K. Okay, so in that case, this Z8 cannot be isomorphic to this H cross K, because Z8 is cyclic, generated by 1. But this won't be cyclic because K will always have order 4, and here any element will have order 2, and here any element will have order 4. So this can never be isomorphic to Z8. Okay, but here this was important for us to declare that this is the only way that we can have G isomorphic to H cross K. That G is actually isomorphic to H cross K. This was the key point which we needed here. Yeah. So I hope this was understood. Is is there any problem in what I said? It will be product of Z5 into Z24 we got from structure theorem, and then we saw that their intersection is identity, and that's why if I take any group of order 24 in G, when I have other H whose intersection is only identity, I can conclude that this H is isomorphic to K. Therefore, G is isomorphic to H and K. I hope this is clear. If not, please ask. Otherwise, we will move to next question. Yeah. Mm. This- Next question is, we have already uh, seen such question, I think in tutorial 9, but I will revise that. That how many elements of order of cycle type, this 5, 2, 2, 1 are there in S10? Okay, note that here 5 plus 2 plus 2 plus 1. So this has to be element in S10. It's not possible otherwise. So what we have a formula for this is that this n, if in Sn the elements of cycle type, the elements of cycle type n1 power k1, nk, ns power ks is n factorial divided by k1 factorial, ks factorial, and n1 power k1, ns power ks. This is the formula which we have. And what this ni imply that this summation k1 n1 is my n, and where summation k1 n1 is n for this relevant, not I. Yeah, we can choose I from 1 to s, and this ni not equal to nj for all I not equal to j. This is the formula. So here what we need to do is, so this 5, 2, 2, 1, I will write this in compact form as 5, 2 square, and 1. Okay, why we are doing this is because when we write cycle type, these are disjoint cycles. None of the number in one cycle is repeated in other cycle. So these are completely disjoint cycle. In that case, if I choose this kind of cycle, for example, if I do this 1, 2, 3, 4, 5, 7, 8, 6, 9, and 10. This cycle is equal to this cycle. Because these are commutative. I mean, these can commute. These two elements are commute because they are disjoint. Uh, we so we can omit this repetitive of cycle. That's why we write it in this kind of compact form to get better idea of the cycles, because we don't want such repetition when we count, when we specially are trying to count the number of elements of certain type. Okay, so this is the formula which we have here. I will just box this for okay, and you can, so we here have n1 is equal to 5, n2 is equal to 2, n3 is equal to 1, and k1 is 1, k2 is 2, and k3 is again 1. So my number of elements of cycle type this 5 to 1 then becomes 10 factorial divided by k1 factorial. So this is 1 factorial, k2 is 2 factorial, and this is again 1 factorial into this, the way we wrote this. This is 5 power 1, 2 power 2, and here again it is 1 power 1. So this will be, if I omit this 5 and 2, so this is 9 into 8, 7, 6, 5. I'm excluding this 4, 5. Yeah, 5. Let it be. Let us keep this. Yeah, 5 is there because 5 was only 1 here. 5. And 4 is gone. 3, 2, and 1. So this is 9 factorial divided by 4. Okay, this is the number, and you can calculate this number if you want, or the I think in the exam there will be virtual calculator. It depends on the type of exam which we are giving. So if there is virtual calculator, you can calculate it, or otherwise the numbers won't be this huge. And I hope you got the idea how to calculate this. I took this S10 because I wanted to repeat these things. For example, and you can uh, please try to what I was saying. Please remember this formula here. We are having factorial of k and then n power k1, the cycle type as it is repeated. So this was one more of an example which I wanted to do. I hope this was clear. And now this next question, question 7. This is what is the order of the following permutation? Okay, and the cycle is 1, 2, 2, 7, 3, 3. 6 goes to 9, 7 goes to 5, 8 goes to 4, 9 goes to 6. And if you want to calculate order of such permutations, the best thing to do is express them in terms of disjoint cycles. Write them in the cycle form. So if I call this sigma, then sigma is what? This is 1 going to 2. Now 2 goes to 7, 1 going to 2, 2 goes to 7, 7 goes to 5, 5 goes to 8, 8 goes to 4, and here 4 goes to 1. That's it. 4 goes to 1. And here 6 goes to 9, and 9 goes to 6. That's it. And I have now this, how many numbers? 6, 2, and 3 is fixed here. So these are the disjoint cycles which I have. And order of this one, and they are what I say. So this is when I say that this is 3 is fixed. What this means is that this 3 is actually not, we can just omit this 3 and I will have this cycle 7, 5, 4 and 6, 9. This is just the same cycle form. This does not change anything. And now these two cycles, if I say this as sigma 1, sigma 2, then this sigma is sigma 1 into sigma 2 and I can permute them. I can commute them. This sigma 2 this is equal to sigma 2 into sigma 1 because these are disjoint cycles. Disjoint cycles, hence commute. And the moment I have two cycles commuting, order of sigma, so C is cycle. So this is cycle of size 6. So sigma 1 is cycle of size 6. This implies that order of sigma 1 is 6 and sigma 2 is a transposition. Sigma 2 is a transposition. Therefore, we have order of sigma 2 is 2. And I have now two elements of finite order who are commuting. Then I can use this formula, right? Order of sigma will be what then? Order of sigma 1, sigma 2. That will be just this order of sigma 1, order of sigma 2 divided by this GCD of order of sigma 1, order of sigma 2. And this will be 6 into 2 by 2, which is 6. So answer here is 6. Okay. So the takeaway from this is that if you are asked to calculate order of any element in the exam for permutation, the best way is to convert them in cycle. The moment I disjoint cycles, I know for cycle of size n, the order of that cycle is n. And the moment I have disjoint cycle, I can commute them. I can, I mean, that product, we can shuffle the order of their product. And then I can use this formula, which we have been using in, I think, first or second week of the course. Okay, this formula. But this works only when two elements commute. Okay, otherwise this does not work. You can try to do this with Sn itself. Sn you choose two elements and such that they do not commute or disjoint cycles. And you can see that order differs. Let us try to do that. For example, I don't know whether this example will work, but let us try to do this. This 1, 2, 3. And if I do this 2, 3, then this will be 2 going to 3, 3 going to 2. 1 is 1 here, 1 is going to 2, 2 going to 3, 3 going to this. I think this 2, 3 and 1, 2, 3. Here also 1 goes to 3. I think this will again be some, oh, let us check. This is going to 3, 2 is going to 3, and 3 is going to 2. So these are still of same order, but you can check some. I mean, these were S3 is very, what I can say. S3 has elements of either size 2 or 3 or 6, right? So there we won't have much, what I can say, uh, much possibilities for order. So go for higher numbers, for example, at least S4, S5 or S6, and try to get elements where commuting those cycles will not give you the required, what I can say, permutation. Sorry, you will get cycles of different size. Okay, so even I gave this, I asked you to do the same, I think yesterday also, that please try to find an example of finite order. Okay, we always, you can go to GLNR where you can take two elements of finite order and their product need not even have finite order. And in such, so we do not have to go to such examples. This is this is no, again non-abelian group. And here I think we saw in one of the lectures already that we got two matrices of something where I was getting diagonal matrix every time I was multiplying the matrix, and it did not have, but the chosen matrices had finite order. I think we did that in tutorial 4. You can try to check. But this is infinite group. This is infinite group. What I'm asking you to do is try to find uh, elements. Try to find let try to find a group of order of finite order and elements order G, say G, and elements A, B in G such that order of A, order of B is finite, but order of AB is not equal to order of BA. And we need to uh, look among the non-abelian groups to find this. Or okay, so I hope this was, for example, you can also check in Q8. Every element has order or of finite order. For example, if I take I, order of I is 4, order of J is 4, order of K is 4, right? Even for minus also it is the similar, right? This is 1 minus 1 and ijk. Order of K and minus K is same there, so it won't be much of a help. Okay, but at least in SN you will definitely get such examples. Okay, if this is there. So next is this example we can do. Meanwhile, if you get any example, please let me know. We'll move to next question, that let G be a group of order 30, then G is a simple group. This is true or false, which we need to check. And how to go about this? That we are given group of order 30 and ask that whether this group is always simple or not. So how to do with this? So if you remember, I wrote this theorem I think in week 8 or week 7 lecture, that I did not prove it. So let us prove this, that if G be a group of order PQR with P less than Q less than R and PQR are primes, distinct prime, distinct is important. Then one of the Sylow subgroup of G is normal. And the moment I have this theorem, what I get is that this 30 is what? 2 into 3 into 6, right? So it is subgroup of order, it is group with order of the form PQR. And the moment I have this information that it is product of 3 primes with each of them is distinct, then I have this theorem that at least one of the Sylow subgroup is normal. This information I have, and the moment I have this information, I can very well say that. So by this theorem, this becomes false, right? So it becomes false because by this theorem, then by above theorem, G, one of the Sylow subgroup of G is normal. And the moment I have some non-trivial group which is normal, this implies that G is not simple, right? I hope you remember what simple is. That a group is simple if the only possible normal subgroups are trivial, subgroup, or the whole group. Or the other way of saying this is that G does not have any non-trivial normal subgroup. This is the definition of simple group. And now we will try to prove this theorem, and let's see how it goes. That so proof, we'll try to cover as much details as possible. Otherwise, so we may assume and even that P less than Q less than R, right? Yeah. And let NS denote the Sylow S subgroup of G. That is the S has only this possibility, P, Q, or R. It could be any of this. We don't know which of this will give us Sylow subgroup. Okay, so for now, let us denote NS. S could be any of this P, Q, and R. Okay, and suppose none of the Sylow subgroups of G. So NS is just Sylow subgroup of G. So for P, I will denote it as NP. For Q, NQ, and for R, I will denote it as NR. So NS is a Sylow S subgroup of G. And suppose I assume that none of the Sylow subgroup of G are normal in G. Then what I have is, then this NS will be greater than 1 plus S, right? This is why the second Sylow subgroup. You can check that. So NS will be greater than equal to 1 plus S. And since P less than Q less than R, and this NP divides order of G, it follows that NP is either QR or QR. Okay, so I'm assuming that none of the Sylow subgroup of G are normal. Then by second Sylow theorem, I get NS will be greater than equal to 1 plus S at least. Okay. And the moment I have that, I will get that this P less than Q less than R, I already have. And in general, the number of P Sylow subgroup must divide order of group. So this NP must divide order of G. But this NS is greater than equal to 1 plus S. This is for all S. Then this happens. Then NP must be equal to QR or QR. Because P is less than Q less than R. And NP, since divide is order of G is PQR and NP. So what is happening here? This is for all S. Then in case of NP is greater than equal to 1 plus P and NP divides PQR. So the only possibilities are for NP are Q or R or QR. This is what I'm trying to say here. This is for all S. Okay, and this is because I am assuming that none of the Sylow subgroup of G is normal in G. Okay, so this information I have so far. So then this Q must be less than equal to NP less than equal to QR. And why this is the case? I mean, at least this has to happen, right? Because NP divides this. I mean, this is by default because NP divides order of group. So NP has these possibilities. So NP is in between Q and QR. That's there. Because I already have Q less than R. This is just basic. This is by default, the choice of NP and Q and R. So similarly, this NQ, if I choose this NQ is greater than equal to 1 plus Q, and then again this NQ divides order of G. So these imply the possibilities of NQ will be what? This will be R, right? This will be R or PR, or this will be R or PR. So therefore, this R less than equal to NQ less than equal to PR. So in short, what I have is this NQ is greater than equal to R. Forget about this PR. This is the possibility for NQ, because again NQ also divides order of G, and NQ is greater than equal to 1 plus Q. P was lesser. The P won't be there unless I'm multiplying P with R. So this information I definitely have, that this R NQ must be greater than equal to R. So only possibilities for NQ is just this R or PR. Okay, it can't be PQR, because NQ is greater than equal to 1 plus Q. If that's the case, it divides order of G, 1 plus Q divides order of G, and so on. So it's not possible, because you can check this, that this is not possible, but we have now these two informations, that Q NP is between this, and Q is greater than equal to R. And the number of Sylow R subgroups must be PQ. Right, this is the only option possible, because again here NQ, so therefore NR is PQ, because NR is greater than equal to 1 plus R, and this NR also divides order of G, that is PQR. So only possibility is this PQR. So note that how we are doing is that I have P less than Q less than R, but I also have this PQ less than PR and all those. The basic comparison of numbers. We are just playing smart with the possibilities of this NQ, NP, and NR. And I get this now. The the number of R silo subgroups in G is PQ. That is the only possibility. So now, if we count the number of elements in each Sylow S subgroup, and we get we get, since PQR are the only powers, only single are available in only single power, and it will be what? NP of P minus 1 plus 1 plus NQ of Q minus 1 plus 1 plus NR of R minus 1 plus 1 will be PQR. Right. This is the only possibility. So this shows that this PQR is, sorry, NP into P minus 1 plus 1 plus, I mean the same I'm repeating here. Let me just copy. Right, and yeah, this is correct. And now this is greater than equal to NP P minus 1 plus NQ Q minus 1 plus NR R minus 1. I'm just omitting those two, which is greater than equal to QP minus 1 plus RQ minus 1 plus PQ R minus 1. How? Using these three, that NP is greater than equal to Q, and here, where is it? The third one. NQ is greater than equal to R and NR is PQ. So NR is PQ, NQ is, NQ is greater than equal to R and NP is greater than equal to Q. So this thing here, we are using this property, these three, which we got. And now when I simplify them, I get this PQ minus Q plus RQ minus 1 plus PQR minus PQ. So this PQ gets cancelled and I get PQR plus this RQ, that is QR, minus Q, here is R, minus R. So from this, we get that. So what I get, that PQR is greater than equal to PQR plus QR minus Q minus R. Right. And then this will give us QR less than equal to Q plus R less than 2R. Right, because this will give me Q plus R greater than equal to QR. So this I am writing here, but since Q is strictly less than R, I get QR less than equal to Q plus R strictly less than 2R. And the moment I have this, so this gives what? QR less than 2R. So this means that Q less than 2. This is contradiction because this P, Q, R are prime numbers. And so this implies this both P, all this P, Q, R are greater than equal to 2. So this is the contradiction which we arrived by assuming that none of the Sylow subgroup of G are normal. Okay, and using this, we have this, that ns is greater than equal to 1 plus s and so on. Okay, so what we did here was we assumed something. We used the Sylow 2 and Sylow 3, Sylow's first, second and Sylow's third theorem to get the hold on NP, NQ, and NR, the number of Sylow subgroups available possible in the group G. Then using that, we counted the number of elements in that group. And we arrived here that PQR greater than PQR plus QR minus Q minus R. And this, using this, I get that this, from this we get directly that PQR greater than equal to PQR plus QR minus Q minus R. And this will give me Q plus R greater than equal to QR. And but since Q is greater than, R is greater than Q, this implies that Q plus R, this 2R is greater than Q plus R. And I'm just using this. now I just readjust this QR less than equal to Q plus R and 2R and so on. And we arrived at this condition that QR is less than equal to 2R, then which gives me Q less than 2, which is a contradiction, that Q is a prime number and it cannot be uh, greater than 2. So this was something which was left as an exercise earlier, but we just proved this. So the answer is false, that group of order 30 will always have a non-trivial normal subgroup in it. And not just 30. You can do this with any group of order PQR. And this is a really important theorem you can keep in mind for if you are trying to give exam, because this is really handy. You do not have to do check much if such questions are asked in exam. So next is this one which I wanted to do. So I think this is question 8, no, question 9. Again, this is true or false. And the question is, the group A5 is simple. This is what asked. I hope you know what is A5. A5 is a alternative group of A S5. It is collection of all the cycles of odd order in A5. So sign of those cycles are positive. Okay, any odd cycle has sign +1, and every transposition and hence even cycle have sign +1. Okay. Sorry, -1. Transpositions have sign -1. Odd cycles have sign +1. Any cycle of size R has sign -1 power R +1. Yes. So A5 contains all the negative, or all the cycles of positive sign. And we also, in fact, proved that Sn is generated by transpositions. And we also use something called as simple transpositions, n plus 1. And we also proved that A5, not only A5, alternating group for any n is generated by 3 cycles. We proved that. We, in fact, gave constructive proof. We showed how we are actually, what I can say, how we are actually writing each cycle as a product of 3 cycle and so on. What we did was, given cycle, we wrote them in transpositions, and for in case of A5 alternating group, we clubbed 2 cycles, and we gave explicit expression how it is written as product of 2-3 cycles. And apart from that, we also proved that uh, any element, any 3 cycle in in AN can be written as product of 2 type cycles and so on. So yes, we proved many theorems in previous lecture in previous lectures, and I mean previous tutorial sessions. Please go through it, at least the PDFs which I have shared, so that it will be helpful. And yeah, so let us try to prove this. So this statement is true, and we, we will try to prove this, and we have enough time. So proof is that let H be a normal subgroup of G. Okay, so if we assume that H has normal subgroup, if H be a normal subgroup of A5, then possible, yes, possible divisors of H are 2, 3, or 5, right? It's what is order of A5? Order of A5 is 5 factorial divided by 2. So this is 5 into 2, 5 into 3 into 2. Wait, 5 into 2 into 3, or 5, 4, 3. Okay. So only possible divisors of possible prime divisors of H is 2, 3, or 5. Okay. So suppose 2 divides order of H. Then what will happen? Then by Cauchy's theorem, there exists an element of order 2 in H. Element say sigma of order 2 in H. That is sigma square is identity. Okay, so since sigma is an even permutation, it must be product of two transpositions, right? So let, without loss of generality, let sigma be 1, 2, and 3, 4. And we also have this, that all the permutations of same cycle type are conjugate and are conjugate of, of each other. And hence, any permutation of the form IJKL, where 1 less than equal to IJKL, are conjugate to sigma. And the moment I write it that this is permutation of the form IJKL, this is by default. I mean, by the definition, the way we have defined cycle type. Okay, so these are conjugate of sigma, And also H is normal in G. So therefore, since every element of this kind, Ij and Kl, are conjugate to sigma, also H is normal in G. This imply every cycle of every permutation of every permutation of the form of the cycle type. Just a second. Ij, Kl are contained are belong to H. Is this clear? Because that's how we have chosen this H. So every conjugate, any Ij, any cycle of kind any 2-2 cycle. Let me call it 2-2 cycle. Any 2-2 cycle is conjugate of sigma. Sigma belongs to H, which is a normal subgroup of G. And the moment, and since it is a normal subgroup, every conjugate will be inside H. But every cycle, every permutation of 2-2 type cycle, uh, every permutation of 2-2 type cycle is conjugate to sigma, and that's why it belongs to H. Okay, we are having this two, that this IJKL is conjugate to sigma plus this H is normal to G. These two facts are giving me that every cycle of 2-2 type belong to my group H, which we started with. Okay, so wait, here they are not including this. So since by writing this 3 cycle 1, 2, 3 as, let us call this tau, 1, 2 and 2, 3, we conclude that this 1, 2, 3 is in H. And again we use, so we started with the sigma of order 2 and we chose the sigma, and from the sigma we arrived here that every permutation of type of 2-2 cycle is in of this kind Ij and Kl belongs to H. Okay, and then from that we came to 3 cycle. 3 cycle we wrote it in the form of product of 1, 2 and 2, 3. And the moment I have that, since H is, yes, since H is normal, since again H is normal, we get that every 3 cycle belongs to H. So we started with the sigma of order 2, then we got any cycle, any permutation of type IJKL, transposition IJKL belong to sigma, sorry, is conjugate to sigma. H is normal, so every permutation of type IJKL belongs to sigma. Then we took a 3-cycle, expressed it in terms of product of two transposition. And since that 3-cycle, once it belongs to my H, again we will use the normal condition of H, and we get that every 3-cycle also belongs to my group H, subgroup H. And since we, as I told you, that we proved that AN is generated by 3 cycles, we get that this H is in fact A5. So this is contradiction, because H was what? H was my Sylow 2 subgroup of A5. So this is contradiction. Now what I need to do, now the two possibilities are, suppose order of H is 3. Sorry. Suppose H is Sylow 3 subgroup, that is order of H is 3. Then since this 3 definitely divides order of H, and hence 3-cycle belongs to this belongs to this group H, and since H is normal, every 3-cycle belongs to H. This again will imply that H is entire A5, and this will again give me a contradiction. So this was clear that 3-cycle subgroup, the moment I have 3-cycle, it will have, since it is group of order 3, it will, sorry. It is Sylow 3 subgroup, so 3 will divide order of H, and then 3-cycle will belong to H. Again, Cauchy's theorem, there exists element of order 3 here, and since H is normal, I will have every 3-cycle belong to H, and the moment I have every 3-cycle belonging to H, I get that H is entire A5. Okay, and the next is for now, suppose H is Sylow 5 subgroup, and sorry, not Sylow 5 subgroup. Suppose 5 divides order of H. This is the conditions which we are starting with. Suppose 5 divides order of H. This is, suppose 3 divides order of H. Then by again Cauchy's theorem, we get that 3-cycle belong to H. Since H is normal, every 3-cycle will belong to H. This will imply H is A5. Now suppose 5 divides order of H. So we are doing this, what I can say, we are, let me use another color. We are doing this, the possibilities that 2 divides H and 5 divides H. These are the 3 possibilities on the divisors of order of H. Okay, so now what this implies then, sorry, then H must contain all the 5 cycles, right? Because 5 divides H. Again, we are assuming that H is a normal subgroup. 5 divides H, so 5 cycle belongs to H. And then all 5 cycles must belong to H, using again the normality of H. So what we are doing is 5 divides H, order of H. Then 5 cycle will belong to H, at least one, using Cauchy's theorem. And then since H is normal subgroup, every 5 cycle will belong to H. So since every 5 cycle belong to H, then there are total 24 of them, right? That total 24 5 cycles. I hope you all know this. If you do not know, go back to that formula which we did. How many elements of certain kind, how many elements of given cycle type are there in group? Okay. Okay, do that. It will be 5 factorial divided by only k factorial. K is 1 here, so this is 1 factorial divided by n power. So this is 5 power 1, so 5. So this is only 4 into 3 into 2 into 1. So there are only 24 possible options. The formula which we used. Okay, so there are 24 of them. We just calculated. We just we just had a calculation. So 24 of them. And since the order of H divides order of A5, that is 60, this implies that order of H must be greater than equal to 30, right? Because what there are at least 25 elements here, 24 elements, 25 elements here, right? Which divides 60. So because 5 cycles plus identity will at least be there. And there are few more elements. Identity is not 5 cycles. So 5 cycles are there. There are 25 of them. And then identity will be there. So at least 25 elements. So, and since order of H divides 60, H is a order of H is a number which is greater than 20, has possibility of being a number greater than 25, which divides 60. Okay, so that is 30. So H is greater than equal to 25 at least. So H must be greater than equal to 30 because H divides 60. So therefore, three divides the order of H, and the moment 3 divides order of H, right, you can check. The moment I have 30, H greater than equal to H greater than equal to. So what we are doing is we are looking at all the divisors of 60. The moment I am looking at all the divisors of 60 and H is greater than equal to 30, it will have an element of order 3 in it. And again, so this will imply that 3 cycle belong to H, then H normal. Since H normal, all three cycles belong to H. This imply that H is entire A5. And again contradiction because H was non-trivial normal subgroup uh, is what we started with. Okay, so this is something we did. So this why we did this is to get an idea how when you are asked certain questions, how to get rid of the possibilities to arrive at the conclusion. That is, we have to prove that A5 is a simple. So if there is any normal subgroup in H, since it is a subgroup of A5, order of then there are possible divisors are 2, 3, 5 prime divisors, and we got the contradiction at each for each prime, that if 2 divides H, we got the contradiction, 3 divides H, we got the contradiction, 5 divides H, we got the contradiction. So this was purely proof by contradiction. But apart from this, please, these are some results which I would like to write here. To we some of these we have proved in our previous sessions, but these I think will be helpful. You can try to prove this using the similar arguments which we did in last two questions, where PQR and for this A5 as well. Okay, this is something which we proved already, and now these are some results which you can, if possible, just memorize them. That let P and Q be distinct primes and G be a group of order P square Q square, then G is not simple. Okay, so if someone asks you, so this result is true, you can try to prove this. And so if someone asks you, any group of order 2 square, for example, if I ask you for 100, n is equal to 100. So if question is that is G with order 100 or let G be a group, order of G is 100, then is G a normal subgroup? Sorry, simple. Is G simple? And from this example here, 100 is what? It's 5 square, 2 square, right? So by this uh, theorem, we can easily conclude that no, a group of order 100 can never be simple. And similarly, we had proved that if G is a group of order P square Q, if you remember, I think in 8th or 9th session, we also proved that a group of order P square Q square is not simple. And similarly, you can go and try to prove this kind of theorems. And yeah, we are anyway over time right now. But yes, these are some kind of questions which you will be asked in the exam. Try to prove, try to go through all the tutorials which we did. Also go through all the assignments which you are given. Try to practice them again and again. And if you have any doubt, please raise them in the uh, Google Classroom, and we are there to help. And prac try to memorize all the formulas and go through such results which I have already wrote a few times. And if you want to understand this group action and other properties clearly, you can follow this book, Algebra by G. Santanam. This is a really good book which has many good examples and all such results of this kind which I wrote here. And you can go through this book and try to understand as many examples as possible. Okay, so thank you and all the best for your exams.